Thank you for pressing play. Your presence here brings joy to my heart. We're thrilled to present to you our video dedicated to bijective numeration. Enjoy. Bijective numeration is any numeral system in which every non-negative integer can be represented in exactly one way using a finite string of digits. The name refers to the bijection, i.e. one-to-one correspondence that exists in this case between the set of non-negative integers and the set of finite strings using a finite set of symbols, the digits. Most ordinary numeral systems, such as the common decimal system, are not bijective because more than one string of digits can represent the same positive integer. In particular, adding leading zeros does not change the value represented, so 1, 1 and 1 all represent the number 1. Even though only the first is usual, the fact that the others are possible means that the decimal system is not bijective. However, the unary numeral system, with only one digit, is bijective. A bijective base K numeration is a bijective positional notation. It uses a string of digits from the set 2. K where K1 to encode each positive integer. A digit's position in the string defines its value as a multiple of a power of K. Calls this notation K-adic, but it should not be confused with the P-adic numbers. Bijective numerals are a system for representing ordinary integers by finite strings of non-zero digits, whereas the P-adic numbers are a system of mathematical values that contain the integers as a subset and may need infinite sequences of digits in any numerical representation. In the next portion, we'll be immersing ourselves in the realm of definition and examining its broader implications. The base K bijective numeration system uses the digit set 2, KK1 to uniquely represent every non-negative integer. As follows: the integer 0 is represented by the empty string. The integer represented by the non-empty digit string is. The digit string representing the integer meters 0 is, where a beginnerlina 0 and equal meters q0k and q0 and equal fifth frac meters chi to 1 and equal q0 q1k and q1 and equal fifth frac q chi to 2 and equal q1 q2k and q2 and equal fifth frac q chi to avots and avots n and equal qn 0k and qn and equal fifth frac qn chi to equal ienderline and fax x1, x being the least integer not less than x, the ceiling function. In contrast, standard positional notation can be defined with a similar recursive algorithm where fax x. The spotlight now falls on extension to integers as we delve deeper into its details. For base K1, the bijective base K numeration system could be extended to negative integers in the same way as the standard base B numeral system by use of an infinite number of the digit dk1. Left K1 represented as a left infinite sequence of digits L dots decayed k Chauvelin k. This is because the Euler summation our overlined k sum I equal infinite k key equal a frac equal, meaning that our overlined k ad k equal ftic sum I equal infinite k key equal 1 sum I equal infinite k key equal, and for every positive number n with bijective numeration digit representation d is represented by Chauvelin k adict. For base K2, negative numbers n1 are represented by Chauvelin k adict with ik1, while for base K2, negative numbers n1 are represented by Chauvelin dict. This is similar to how in signed digit representations, all integers n with digit representations d are represented as Chauvelin with 0. This representation is no longer bijective, as the entire set of left infinite sequences of digits is used to represent the k-adic integers, of which the integers are only a subset. Our focus now turns to properties of bijective base K numerals, an important aspect of our discussion. For a given base K second number of digits in the bijective base K numeral representing a non-negative integer n is logcan erc, in contrast to logcan for ordinary base K numerals. If k equal 1, i.e. unary, then the number of digits is just n, the smallest non-negative integer representable in a bijective base K numeral of length 0 is Marfminel fracile erk, the largest non-negative integer representable in a bijective base k numeral of length 0, is Marfmaxile fracile kirk, equivalent to max k-min, or max min 1 1. The bijective base k and ordinary base k numerals for a non-negative integer n are identical if and only if the ordinary numeral does not contain the digit 0 or, equivalently, the bijective numeral is neither the empty string nor contains the digit k. For a given base k, first are exactly bijective base k numerals of length 0, a list of bijective base k numerals, in natural order of the integers represented, is automatically in short lex order shortest first, lexicographical within each length. Thus, using to denote the empty string, the base 1, 2, 3, 8, 10, 12, and 16 numerals are as follows, where the ordinary representations are listed for comparison. Bijective base 1, 1 11 100 and 11 11 11 11,000 111 111,000 111 1,000,000 111,000 111 11,000,000 111,000 111 111,000,000 111,000 111 1,000,000,000 111,000,000 111,000 111 11,000,000 111,000,000 111,000 111 111 billion 111,000,000 111,000 111 1 trillion 111 billion 111,000,000 111,000 111 11 trillion 111 billion 111 million 111,000 111 111 trillion 111 billion 111 million 111,000 111 1 quadrillion 111 trillion 111 billion 111 million 111,000 111. Unary numeral system bijective base 2 1 to 11 12 21 22 111 112 121 122 211 212 221 222 11 11 11 12 binary 0 1 10 11 100 100 and 1 110 111 1000 1000 and 1 10 10 10 11 1100 11 01 11 10 11 11 10,000 bijective base 3 1 2 3 11 12 13 21 22 23 31 32 33 111 112 113 121 ternary 0 1 2 10 11 12 20 21 22 100 100 and 1 100 and 2 110 111 112 120 121 bijective base 8 1 2 3 4 5 6 7 8 11 12 13 14 15 16 17 18 octal 0 1 2 3 4 5 6 7 10 11 12 13 14 15 16 17 20 bijective base 10 1 2 3 4 5 6 7 8 9 11 12 13 14 15 16 decimal 0 1 2 3 4 5 6 7 8 9 10 11 12 13 14 15 16 bijective base 12 1 2 3 4 5 6 7 8 9 b Celsius 11 12 13 14 decimal 0 1 2 3 4 5 6 7 8 9 b 10 11 12 13 14 bijective base 16 1 2 3 4 5 6 7 8 9 b Celsius d East Fahrenheit g hexadecimal 0 1 2 3 4 5 6 7 8 9 b Celsius d East Fahrenheit 10. Get ready for a thought-provoking discussion as we delve into examples and its impact on our understanding. 34,152 in bijective base 5 equal plus equal 24 27 in decimal. Here in bijective base 10, with a representing the digit value 10 equal plus 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 equal 1200 in decimal. A typical alphabetic list with more than 26 elements is bijective, using the order of A, B, X, Y, Z, AA, AB, AX, ZY, ZZ, AA, AAB, AAC. Get ready for an exciting exploration as we unravel the mysteries of the bijective base 10 system. The bijective base 10 system is a base 10 positional numeral system that does not use a digit to represent 0. It instead has a digit to represent 10, such as A. As with conventional decimal, each digit position represents a power of 10, so for example 123 is 100 plus 2 tens plus 3 units. All positive integers that are represented solely with non-zero digits in conventional decimal such as 123 have the same representation in the bijective base 10 system. Those that use a 0 must be rewritten, so for example 10 becomes a conventional 20 becomes a conventional 100 becomes a conventional 101 becomes a conventional 302 becomes a conventional 1000 becomes a conventional 1110 becomes AAA, conventional 2010 becomes EO, and so on. Addition and multiplication in this system are essentially the same as with conventional decimal, except that carries occur when a position exceeds 10, rather than when it exceeds 9. So to calculate 643 plus 759, there are 12 units right 2 at the right and carry 1 to the tens, 10 tens right with no need to carry to the hundreds, 13 hundreds right 3 and carry 1 to the thousands, and 1000 right 1 to give the result here rather than the conventional 1402. Moving forward, we'll be taking a closer look at the bijective base 26 system. In the bijective base 26 system, one may use the Latin alphabet letters A to Z to represent the 26-digit values 1 to 26. A, B, K, S. With this choice of notation, the number sequence starting from 1 begins A, B, C, X, Y, Z, AA, AB, AC, AX, AY, AZ, BA, BB, BC. Each digit position represents a power of 26, so for example, the numeral WI represents the value equals 607 in base 10. Many spreadsheets, including Microsoft Excel, use this system to assign labels to the columns of a spreadsheet, starting A, B, C, Z, AA, AB, AZ, BA, ZZ, AAA, and so on. For instance, in Excel 2013, there can be up to 16,384 columns in binary code labeled from A to XFD. Malware variants are also named using this system. For example, the first widespread Microsoft Word macro virus, Concept, is formally named Conceptor. Its 26th variant Concept, the 27th variant Conceptor, etc. A variant of this system is used to name variable stars. It can be applied to any problem where a systematic naming using letters is desired, while using the shortest possible strings. Now, let's redirect our focus towards historical notes and discover its significance in our narrative. The fact that every non-negative integer has a unique representation in bijective base KK1 is a folk theorem that has been rediscovered many times. Early instances are for the case k equal 10, and for all k1. Smullian uses this system to provide a dual numbering of the strings of symbols in a logical system, uses these representations to perform computations in the programming language P, mentions the special case of k equal 10, and discusses the cases k2. Appears to be another rediscovery, and hypothesized that if ancient numeration systems use bijective base k, they might not be recognized as such in archaeological documents, due to general unfamiliarity with this system. Your feedback helps me improve, so please take a moment to leave a comment or review.